Shaheen and I are both really excited to have somebody generally regarded as a rock star of storage. He's Gary Grider.
I actually find that probably be one of the most interesting things that's happening right now is that the distributed database people and the really forward-thinking HPC analytics people are headed towards the same place.
From Orion X in association with Inside HPC, this is the At HPC podcast. Join Shaheen Khan and Doug Black as they discuss supercomputing technologies and the applications, markets, and policies that shape them. Thank you for being with us.
Hi, Shaheen. It's great to be with you again.
Good to be here, Doug. How are you?
Very good. Thanks so much. So we're going to start off this episode with a quick review of some of the more important news of the week in HPC and supercomputing.
Top of the news.
Exactly. Quantinuum, the quantum development company, announced the system model H1-2 doubled its performance to, quote, what they say, become the first commercial quantum computer to pass quantum volume 4096.
Nice.
Yeah, which is a benchmark introduced by IBM 3 years ago to measure overall capability and performance.
Yes. So a quick reminder that Quantinuum, as many of you know, is the merger of Honeywell's quantum computing effort with Cambridge Quantum Computing out in the UK. And they've been very good in quantum volume. Now, there are two metrics that measure performance for quantum computing right now. One is quantum volume, which, as you mentioned, IBM proposed in 2017 and has taken, and it's just really good work. So that one is about the maximum size of a quantum circuit, which is a function of the number of qubits. How many qubits do you have to even build a circuit from? And how noisy, what's the quality of these qubits? What's their fidelity and what is their connectivity? And because trapped ion, the methodology that they use, is especially high fidelity, they really score highly there. Now, there's a new metric that IBM also proposed just a few months ago, back in 2021, and that's a CLOPS, for circuit layer operations per second, which takes the scale, the number of qubits and quality, the depth of the circuit as a function of fidelity and connectivity, and adds to it speed. Just how fast can I execute these circuits? And that one is still a developing metric, but all of this is an effort to try to get closer and closer to what matters to the end user. So good job on Quantinuum.
There's a steady stream of news coming out of the quantum community. The running joke that quantum is one of those technologies that will always be 10 years away. I think we might be getting down to it'll always be, say, 3 to 5 years away. So.
That's right. It's significant progress.
Yeah, there we are. Now, DOE had two pretty significant funding opportunity announcements that relevant organizations might want to look into. $40 million over 4 years for fundamental mathematics research. This has to do with the integration of multiple mathematical topic areas that will result in the Mathematical Multifaceted Integrated Capability Centers, MMICCs.
Nice. The part of that resonates with me is the word multifaceted, because that implies and is the multidisciplinary approach, a more holistic way of looking at problems. And we can apply that across the workflow because it's multifaceted by definition, or go deep and try to cover the pieces that maybe some years ago you'd made assumptions about that you can come back and now be more accurate about. So all very, very good. And of course, math continues to be the track and field cross country of science that if you're good at it, you can be good at everything. So that's very good.
Yeah. And then there's a $26 million funding opportunity. This is for research on scientific data management and visualization over 3 years. Both of these opportunities, by the way, are sponsored by the Office of Advanced Scientific Computing Research, ASCR.
Beautiful. It is definitely an indication that governments around the world are investing in technology because they recognize how important it is to the future of the nation.
Yes. Moving on to our next story we had in Inside HPC. This was an article based on coverage in the Wall Street Journal about the war crimes investigations now undergoing in Ukraine. According to the journal piece, there's 1,000 people involved in investigating alleged crimes in Bucha, which is a Kyiv suburb. And they're using a lot of the techniques that are in the HPC world, HPC AI. This would be advanced machine learning technology, facial recognition, geospatial data analytics, image analysis, and certainly analysis of streaming video from security cameras.
Yeah, I read that article. Very, very interesting. The other thing that was probably new in the scene is the notion of an open source intelligence, OSINT, which on the one hand is good because you can provide a lot of intelligence from just people and security cameras and such, as you mentioned, but it's also the challenge of verifying it and cross-referencing it and fact-checking it and all that. But it's a brand new day in that sort of forensics.
Well, in doing this story, a lot of what they're doing to me was a direct echo of some of the techniques used by brick and mortar retailers to understand consumer behavior and also to track repeat customers and make appeals to them in real time. But in any case, it's using, again, facial recognition, et cetera, in this case, to track and investigate really the grim details of these war crimes. So,
yeah, those of our listeners who listened to our episode on cyber warfare when the war broke out first, remember that we said we were not really seeing evidence of that quite yet, like what happened. And sooner or later that was going to happen. And of course, it is happening now in various forms.
yes, indeed. And then finally, our big news of the week was from TSMC. They put out quarterly earnings that were very impressive. In US dollars, first quarter revenue was almost 18 billion, an increase of 36% year over year.
That's right. It was very interesting. Obviously, you'd expect TSMC to do well because they're just
a juggernaut. Yeah.
What was interesting to me there was that they look like they have the lion's share of the market share at the high end. According to some analysts, 90% of the high end, depending on how you define high end. And then they grew 70% in automotive. I think that's in part because they probably redirected some capacity for automotive because of the supply shortages around the world. Also because there's a big indigenous market in China for automotive chips. And in fact, they showed 149% growth in China. That's compared to 30% growth in North America. The second growth was HPC AI, 59%. Now, I think the growth in HPC and AI is off of a bigger base and therefore a lot more significant, although automotive is a really big market. And then IoT was at 21%. The other thing that was notable was that their quarterly capex was $9.4 billion, a new record, and just the level of investment that you need to be prepared to compete with if you're trying to compete with them.
Well, it's this turnaround story that's really about 5 years old now, just continues to roll. It's really impressive.
One should expect that TSMC will continue to execute. One can also expect Intel to catch up because obviously they too have been investing money and resources and technology in different ways, including packaging, where they are extremely strong. So they have the wherewithal to do this. And in fact, their 10 nanometers was more like 7 nanometers by others. So it's very familiar ground. They don't have to start from scratch or anything like that. And then two, TSMC is in the frontier. So they're facing problems that haven't been solved before. And in principle, that could be more challenging and allow folks to catch up with them. And the third player is Samsung, and they also have been gripped with some challenges according to some news, but they continue to be number 2 there in terms of node size.
Okay, so now to our main topic. Shaheen and I are both really excited to have somebody generally regarded as a rock star of storage. He's Gary Grider. He's the HPC division leader at Los Alamos National Laboratory and has been instrumental in the development of really significant advances in high-performance storage over the course of his career, which began at Los Alamos in the late 80s. Gary, it's really a thrill to have you with us.
Thank you for having me.
The last time I spoke with you was in September of 2020, but I wanted to ask you to begin with, maybe if you could talk about some of the major developments in HPC storage, HPC class storage, that you've been involved in over the last decade or so.
Okay, well, probably is going to have to be a little longer than last decade since I've been in it for like 4 decades. So probably one of the things that I'm most famous for, I guess, is Lee Ward and I from Sandia went to DOE and got the money to do Luster. And we worked with Peter Brahm for 4 years to get Luster out the door, starting in about 2001 to 2005. And of course, Luster has become quite a used thing in HPC. So I guess that's a pretty big deal. Also, another thing that I was involved in pretty heavily was we had in the DOE NNSA ASCII program, we had this thing called the Alliance programs, which is partnerships with universities. And again, Lee Ward and I started an effort at University of California, Santa Cruz to build an object-based user space prototype parallel file system that we could use to do research on scalable metadata and scalable security and all kinds of things. And it's interesting that project, they started out and said they needed to do about a 3-year buildup of this prototype infrastructure, and then they would do research for us for the next few years. And we ended up funding them for 9 years, and they built what's now called Ceph. So I think that's kind of interesting as well. So we spent an awful lot of time with Sage and professors there at UC Santa Cruz working on what that should be and what it should be used for. And we wanted to use it as a research vehicle, but they had other ideas, and that worked out great. So, and then of course, probably more recently, things like burst buffers, and I'm pretty proud of this new index technology that we've put out that got an R&D 100 award and a bunch of other awards called Goofy Grand Unified File System Index, which is pretty slick, a couple of orders of magnitude faster than just about anything out there on indexing file systems and looking for things.
Great stuff. The last time we spoke, interesting theme that emerged. You were saying at that time that in HPC technology and also in the community, your biggest concern was that traditional, big, extremely complex simulation work was kind of falling by the wayside in favor of emerging HPC areas such as AI and quantum. I'm interested if how your thinking on that issue has evolved over the last 2 years.
A little bit. I mean, I still think it's a huge problem. Chasing the almighty flop has really gotten us off into a space that doesn't serve complex simulation very well. And then AI came along and kind of made it worse by wanting to use not even 64-bit integers or floats and doing, pretty dense calculations. There's certainly some deep neural networks and things like that are sparse and similar to simulation. And I think at some point, this is probably going to sound mean, but they'll run out of what I would call low-hanging fruit kind of, activities where it's really fairly simple, pretty embarrassingly parallel, pretty dense kinds of calculations that are pretty typical of AI and machine learning training, at least. And they'll eventually take on things, and I think some of them are already on far more sparse, irregular kinds of memory patterns and things, more like simulation than current. And so I think we're still waiting sort of for the steam to run out of the low-hanging fruit piece of AI and ML. I mean, I liken this to Hadoop a while back, right?
Mm-hmm.
Hadoop was a little low-hanging fruit version, and eventually they ran out of low-hanging fruit and had to move to Spark.
Right.
I think that's going to happen. I hope that happens in the AI ML world as well, because it'll bring back a more balanced approach to computing architectures besides just dense linear algebra, which solves some problems, but not all that many, actually. And so I think I'm happy that people are starting to recognize it. Actually, Dan Reed wrote a nice piece recently on this very topic.
Dan was a guest, actually, a couple of weeks ago.
Well, it wasn't. He was out a few weeks ago here, and I talked to him occasionally. And he was lamenting, similar to me in this regard, thinking that we could move towards tailoring and other kinds of things that are other trains that can be leveraged besides just the AI train, and maybe get some more balance back in architectural pursuits that suit more than just fairly narrow, dense linear algebra kinds of approaches. So I think I see the low-hanging fruit starting to wane a bit, and I see people starting to think about sparser, more irregular problems like ours.
I really like the way you described that. And of course, in addition to the computational part of AI, there's also a movement about data-centric AI that Andrew Wynn and company have been driving to highlight the importance of quality of data. We touched on it a bit last week in our podcast. I'm hoping that would also underline the importance of storage and data movement and data flow. How do you see that impacting storage from an AI standpoint?
It's interesting. The large-scale simulation was written, most of the codes were written in the era of disks, of course, and parallel file systems grew up around them, and they were all written to do big block IOs of various kinds in massively parallel ways. So things like Lustre work pretty well for that. That's what they were made for. But the AI frameworks are really quite different. They grew up very differently. They grew up not as parallel. They grew up as a single machine to start with, and some of them had to go parallel. A lot of them are just ensemble-like things. They're single machines with just a whole lot of ensembles to get the work done. You find the people that use those frameworks kind of grew up around local file system look and feel. So If you think about it, how fast your local file system is to do an LS or whatever compared to Lustre, it's always going to be faster because Lustre wasn't designed for that. It wasn't designed to have local feel and local latencies and things. It was designed to have a million processes all open up the same file at the same time and write to it at the same time. And it's a radically different thing to do. And so I find that the solution space is kind of, at least right now, diverging. And you see things like Weka and Bast picking up on this. Oh, crap, we need to do millions of small files and we need to make it feel and look like it's pretty local. And there's other approaches to doing that, like putting local flash right in the compute nodes or running simulated local flash over NVMe over Fabric or things like that. And I think right now we're sort of in an era where a site that has to support both heads down hardcore simulation like at LANL, which is probably 80% of what we do, and some amount of AI and ML, you kind of have to have two solutions for that space right now because they just grew up very, very differently. And it's kind of unfortunate, but it's interesting, right? Because your workload morphs from month to month or quarter to quarter or whatever, and more of it is AI for a while, maybe more of it simulation for a while. We really need to get to the point where we can add more Lustre when we need to and take away Lustre and add more other kinds of storage systems that work well with these small file workloads and things, and change our mind occasionally. It'd be nice if we could change our mind on a per job basis, but we're nowhere close to that. So I kind of see NVMe over Fabric making that all possible, just like Fiber Channel did. I don't know if you remember a long time ago, right? You put disks inside of the nodes, and then Fiber Channel came along and you took the disks out and disaggregated them. Well, that's happening again, right? I mean, NVMe over Fabric is the modern day Fiber Channel. And in fact, a lot of the people, came from that world that are in the standards bodies and things. And so, with disaggregated storage, one can contemplate having just a big pool of storage, and you can change your mind about what storage service you want to provide with the backing store. So imagine having a whole bunch of compute nodes that do the compute, and then you have a pool of storage services nodes, and they're not all Lustre anymore. There's some Lustre nodes, and maybe there's some XFS or Weka nodes, and maybe there's some key value nodes and other kinds of things. And they consume the pool of NVMe over Fabric Flash. And sites can change their mind from time to time about how much is applied to which thing based on their workloads and the like. So that appears to be kind of where we're headed in the very, very short term. Longer term, there may be some convergence around key value. I don't know. We think that that's possible because ultimately almost all these things are really records. Even the petabyte size data sets we write out, they're not streams of bytes, they're records. There's 50 floating point values per cell within a mesh, and there's a trillion mesh cells, and so you have a trillion records. We never wrote it out that way. We always wrote it out serially because we had disks, but clearly, most things actually are record oriented in some way or form. So we think that the world may converge eventually on records, which is really super interesting because when I was first starting out, we used VSAM, which was a access methods, right, which was record oriented. So it's come full circle. It's just taken 50 years.
Is that the same as the semantic web and everything is a graph and tuple space and things like that?
It is very similar to that, right? It's probably more like for us, for simulations, it's probably a bit more like geospatial. So the geospatial people took things like SQLite and I don't know, there's several of the databases, MySQL and all those, and they added geospatial querying and storage capabilities to them.
Well, they have their own formats too now.
They have their own formats. And even there's variants on like Apache Drill that will do geospatial and stuff. And why is that interesting to us? Well, if you think about it, a physics model running, is a physical thing and it's 3D shape of some kind, right? And so it has, geospatial dimensionality to it. And any query you do is likely to involve at least the geometry of it. Probably also involves something else like pressure or temperatures. If you're trying to find an isosurface across in front of a shock wave, right, that you're trying to track, that's really kind of no different than trying to find a river and figure out what.
Oh, how interesting.
I mean, it's not terribly different, right?
Yes.
They're quite similar, and it's all 3, 4, 5 dimensional kinds of indexing kinds of problems. And of course, at our scale, distributed joins, which is what this really is, the ultimate hard problem for the database people. I mean, I think we're converging with them. I really do. I think they're finding out that they can use our vector engines by going to columnar stores and all that kind of stuff, which is cool. And they're finding out that the hardware scatter gather that we put in long ago for our vector,
Yes.
works very well with distributed joins and things like that. So I actually find that probably be one of the most interesting things that's happening right now is that the distributed database people and the really forward-thinking HPC analytics people are headed towards the same place.
And sometimes they've been there before, and it's a rediscovery of what we did years ago.
Except at the scales we're talking about.
Except at this scale, right. One thing that comes to my mind when you describe this is the emergence of this whole distributed, decentralized from device and testing equipment all the way to simulation. So that I'm hoping is a forcing function that says that because applications are now workflows and storage is now data flow, that there's an opportunity to have the cake and eat it too. Do you see that sort of an integration, and how does that play in a world where we have a cloud that is acting like a black hole of sucking all the application and data into it, but then there's also a proliferation of devices that are spewing out a lot of data, and how do we balance the two sides of that equation?
I'll try to answer one of those 9 questions.
All right.
We actually saw this with Trinity back in 2016 with the burst buffers, right? As I said earlier, we need to be able to sort of orchestrate over a slow period of time how much storage is applied to which kinds of services that you need. We also need orchestration for users to be able to compose workflows that use multiple storage type services at the right times and stuff as well, right? And that work at LANL actually started before Trinity, and it got serious with Trinity. And why do I say that? So Trinity was the first really, really large burst buffer, and it was 4 petabytes of flash that ran at 4 terabytes a second or something. So
nice.
It's still pretty world class.
Oh, yeah.
And of course, the machine had 2 petabytes of DRAM, which is still the biggest machine in DOE from a memory point of view. But at any rate, Cray, which is now HPE, built this sort of orchestration layer called Data Warp that essentially you put in JCL into your job scripts. And you said, I'm going to need X amount of ephemeral storage that goes this fast and has this number of IOPS, and I'm going to need access to this kind of Lustre stuff. And it's, oh, by the way, I've migrated that stuff off to some, lower tier, like our campaign store or something. And so get it back before you start the job. And, all this stuff that used to be done in JCL back in the 70s. Essentially, it's the same thing, except, of course, in massive parallel and lots of different services. But we were composing workflows that had different kinds of storages in them back then, and we still are. And we expected that to continue. And just the number of services that are out there to do things for you are going to go up by a small amount. And so I don't want to say that's a solved problem within an HPC site, but it kind of is, because, the job scheduler integrated with this orchestration layer, enables you to go do these things today. How do you wrap that around an instrument that's shipping you data and the like? That's actually what NERSC did with their burst buffer. They did 2 things. They put their small file workload on it because Lustre isn't any good at that because it wasn't invented for that. And they also pulled data from Slack. That's sort of I want to call it a trickle, because it's not, I think terabytes per second are interesting and gigabytes per second are kind of trickles, but they're still pretty large. And so data came in from Slack and they buffered it on the burst buffer, and then they had a trigger set, and every so often something would kick off in parallel and just go clean all that up, learn what they were going to learn from it, reformat it, do science on it, and write it back out again and clean it. And I think they still use that. And so there's certainly examples within the Cray Data Warp family of things that have led us in that direction at our behest. I mean, we asked them to write it. We told them what we wanted. Mm-hmm. And it's probably the premier example of a company that provides an orchestration layer combined with a scheduler, the scheduler of your choice. And you can compose these complex workflows that have different storage things in them. How do you extend that all the way out to cloud and stuff? I'm probably not the right person to ask that. We don't do much of that because of almost everything we have is real secure. So we don't really have that much cloud for 2 reasons. One, the classification of it. And if you think about, it's not just the classification that's a worry for us, right? It's the fact that our secrets have value for like 50 years. Where that's not
Uh-huh.
really true for a lot of sites, right? A lot of sites, the spy casing some joint, right? The video of that's only good for a little while, maybe
Right.
a day or two, right? But nuclear secrets, we've been protecting them for 50 years, and they will probably protect them for another 100. And so the problem is that with data like ours, you could replay, that data 40 years from now when the computers have all changed. And so it's not just how secret is it, it's how long do you have to keep it a secret. And so us pumping a lot of data over wires across the world just isn't very wise.
Yeah. Yes.
Okay, Gary. Now, looking ahead 3, 5, 10 years, what are some big developments in storage that you're anticipating?
Well, NVMe and Flash, of course, have changed our world fundamentally because of the sort of 3 orders of magnitude better latency. So certainly you can contemplate way different things than you've ever done before. But another thing that's pretty big, that's growing real rapidly in the non-HPC world is computational storage and computing in the network both. They're both getting to be pretty big things for, like I say, non-HPC sites. We're particularly interested in it for HPC, of course. And so well, you might ask, well, what would you offload if you offloaded to computation or storage? And of course, the win is obvious, right? You move less data and you move it less distance. But we're sort of the poster child for that. And you might say, geez, I wonder why would I say that? Well, if you think about it, my example of the simulation before was, a shockwave going through a material, and you're really interested in the front of the shockwave and where it's at and what it's doing. And if you think about that, that's a very, very, very small fraction of the data that's in each petabyte that gets churned out of one of these machines. It's just the front of the shockwave, right? And so it's probably 1,000th or a 10,000th of the data. And so if you're doing analytics and you're trying to follow a shockwave, you really don't want to move a whole petabyte back into the computer and find the shockwave. You'd rather index the data in some way where you can get only the data you want when you need it. And so you move it 1,000th or a 10,000th of the data. And we've done some interesting demos of this that are pretty simple. We did one with the particle and cell code where there was 1,000,000 cells and 1,000,000,000,000 particles, and the particles fly around within the cells, and because something's forcing them to fly around. And at the end of this, week-long adventure with lots of time steps, maybe one per hour or something, so writing out a petabyte every hour, the scientist comes and says, 1,000 of those trillion particles are really super interesting. Can you tell me where they were? Can you tell me the track that they took through the cells? And we looked at that and said, that's really, really simple. Particle ID is really easy to shard. We can build a sharded index over this and shard it as many ways as we want. So I think we went about 10,000 wide. So we had 10,000 indexes. It was just software. It was just 10,000 like RocksDBs or level DBs. And we were just inserting records. The application thought it was writing files. They wanted to write a file per particle per time step, which is 1,000,000,000,000 files per time step, which kind of wouldn't work, right? But we wrote a little library, and they thought they were writing files, but really they were writing records. And then when they were all done, and of course the key was particle ID. And so it was just super simple. Way less than a second, we could give them where the particles had been because we indexed it. And so that's a trivial, simple example of how just writing the data out as records with a one-dimensional index is a huge win. Now, of course, that's a dirt simple problem, right? It's crazy simple. Really, it's not a bunch of cubes. Really, it's a bunch of 3D tetrahedrals, and the sizes of the volumes inside them are changing all the time because the AMR, the automated mesh refinement, is changing the sizes of things around all the time. And you usually wouldn't ask just, where's the high pressure in the sense of what cells it was in. You would be looking for a wavefront or something like that you're trying to track. And then you may want to try to index against a variable that isn't quite so simple to shard, like location, like you want to index on pressure. Well, if you wanted to index on pressure is changing all the time. Every time step, pressure is changing all over the place, right? And so how do you even know what the distribution of the keys look like to be able to shard it in any reasonable way? There's an interesting story behind that. We actually said, well, gosh, we're doing AMR and we're doing time steps, and every time step, every process exchanges its boundary conditions with its neighbors because that's the way simulation works. Mm-hmm. And actually, if you think about it, in AMR, where the fun stuff is happening, which is likely to be what you're interested in, it exchanges information even more because there's less information going on in each particular piece because the pieces are smaller where the fun stuff is happening. And so we realized that most of the interesting information about the pressures or temperatures or whatever variable you're trying to build an index over is seen by the network. Like 20, 30, 50% of the data is seen by the network every hour or every second or however long your time steps are. And so you can just program an IC to say, keep me a histogram of this particular variable within these records that I'm sending around to my neighbors. And then I'm going to ask you after a few hours what you think the distribution looks like. Tell me what those histograms said. And I can then take a pretty good first shot at what the distribution of the keys is so I can shard it. So then I can write an index out. It's not full of hotspots because I couldn't figure out how to shard it. And so that's both an example of computation and storage where the storage is creating the index on the fly. And it's an example of computation in the network. I had to move the data anyway. I might as well just keep some histograms and get it for free. That's another dirt simple example. Really things aren't quite as simple as what I'm saying, but of how computation in the network and computational storage can really change radically how fast you can analyze the data that comes out of these things. Because you're really only looking for a tiny amount, but you've got to be pretty innovative about how you build indexes on the fly. That's non-trivial. And you don't want to slow it down, right? You don't want to slow the calculation down by indexing on the fly, which is another reason to offload it to storage in the network.
This reminds me of the old definition of a supercomputer, that it would make a CPU-bound problem an IO-bound problem.
Yeah.
And in this case, computation is actually at the service of storage management rather than the other way around. Yeah.
Yep, that's right. I think computational storage and computation in the network is going to be interesting. I think that there's clear wins in the analytics side of the world because of moving the data around or lack thereof. And I think keys and key values and indexes and multidimensional indexes and histogramming and all that kind of stuff is all fair game for that. And oddly enough, that's not terribly different than the rest of the analytics world. If you go look at like Parquet and Apache Drill, they do similar things, right? They have histogramming and, it's columnar instead of rows, but it's just, similar concepts and actually even similar scales sometimes.
A bunch of this is because, like you said, moving data is expensive.
Yep.
Now, this reminds me of grid computing, which the HPC community started and led before it morphed into cloud, that word again. Do we see any benefit from some of that work that we did in the old days to help alleviate the data movement?
What's happening in the open science world in that space, which I don't really live in, but what's happening in that space is people are shipping process to where the data lives and doing a reduction there. So there's lots of examples of that where services are put up for, we don't offer up, download all the data from the human genome, right? We offer up a service that you can do a query and get a subset, and we'll give you the subset because we can't give you the whole thing because you can't handle the whole thing, right? And
right.
So that actually is pretty rampant in open science. That's kind of how it's done out there nowadays.
Oh, interesting.
That's an example of what we learned a long time ago with visualization over the net, over a WAN taught us that, right? You don't ship the data, you ship the polygons.
Right, that's right.
Right, and so it's the same concept.
Yes, excellent. So one near final question for me is, why is storage so hard? Or what did you do to make it easy for you? Rather?
Well, storage started out really, really hard because it was so many orders of magnitude slower than the rest of everything else, right? If you think about a millisecond, or it used to be many, many milliseconds to do a seek, even compared to processors 20 years ago, that's still pretty crazy slow, right? And so it's that 6 orders of magnitude difference in performance between a mechanical device and a non-mechanical device that is why it was so hard to start with. I wouldn't say it's easy now because I think there's 2 things that make it hard. One is that, you're faced with devices that are way slower. Even with flash, you're still faced with devices that are way slower. They're just not as bad. But you've got classical problems that creep in there, like persistence is way harder than not, right? So if you're just a computer and you can just reboot and start over, who the hell cares? But you can't do that in storage. right? You
Mhm.
can't lose people's data. And so there's persistence issues, and persistence at our scales is hard. But you know what? The classical problem that we all still have was we all want to read the damn data, but we don't want to read it in the order we wrote it in. That's true in storage, and it's true in memory. That is exactly my problem with these complex simulations is I don't read the data the way I wrote it. That's crazy, right? I mean, it's this sparse, irregular pointer chasing kind of junk that kills my efficiencies and makes these GPUs and things like that almost useless to me because I can't build a dense problem that they're good at solving. And so it's actually very similar, right? It's basically the age-old problem. Database people have this in spades too, right?
Mm-hmm.
You know, you write the data out one way and you never want to read it the way you wrote it. And that's hard. It's always been hard. I don't know if it's ever not going to be hard.
Yeah. This is endless, which is part of the reason I like it so much.
It always leads to the next question. I guess we'll wrap this one up. Gary, great to be with you. Always great to be with you, Shaheen. And Gary, we'd love to have you back sometime.
Yeah, thank you. Absolutely.
Yeah, thank you for the opportunity.
That's it for this episode of the At HPC podcast. Every episode is featured on InsideHPC.com and posted on OrionX.net. Use the comment section or tweet us with any questions or to propose topics of discussion. If you like the show, rate and review it on Apple Podcasts or wherever you listen. The At HPC podcast is a production of OrionX in association with Inside HPC. Thank you for listening.